Welcome. So the first talk today is by Prahladh Harsha from Tata Institute of Fundamental Research, Mumbai. And it's on PCP compositions, constructions.
Meena and Rahul for arranging my wonderful workshop. So I'll be speaking on PCP composition. This is work I've been doing for nearly a decade. It's based on three joint work, one with Bensason, Bulreck, Sudan and Wadan, another with Erit, Dinur, and most recently with Dinur and Kindler. So when actually Rahul and Meena approached me for a talk, I was inspired to base on it on a recent work which is yet unpublished, joint work with Erit Dinur and Guy Kindler. So I wanted to talk about the most recent works, but as I started preparing the slides, I thought I'll give a more survey article. I'll actually barely touch on the most recent work, and I'll be talking about fairly prior work for most of the time because I wanted to give a survey of what's the role of composition in PCP constructions. Because I realized most people in this audience possibly haven't seen this aspect of it, but for those who have, my apologies. I hope there is something new in this talk. Let's begin. So let's start off with sort of what is like the equivalent of SAT for hardness of approximation, the label cover problem. So what is the cover problem? The label problem, the problem is specified as follows. You're given a bipartite graph, and you're given two sets of labels, sigma 1 and sigma 2, and you're given a set of constraints on every edge in this graph. Constraints are of this form. It's a sort of a map from the first label set to the second label set, and you are asked to color the vertices of both sides, vertices of this side with labels from sigma 1 and vertices of this side with labels from sigma 2, such that you satisfy as many edges as possible. For instance, this could be like some examples which you already seen in this conference. These could be various 3-sat clauses. These could be variables, and I have an edge from a 3-sat clause to a variable if that variable participates in the clause. And you have one of 7 labels for the 3-sat clause, which tells you which of the 7 satisfying assignments of the clause it is. And this is exactly the projection constraint. It says if it's one of those 7 satisfying clauses, 7 satisfying assignment, what's the corresponding assignment to the variable? So this sort of encodes several NP-complete problems which we have can be encoded this way. And the goal is to find a labeling that satisfies as many edges as possible. So let's actually that's it. So we'll define our problem. So problem will be, I'm going to give you instances of this problem and ask to distinguish between instances which are completely satisfiable, that is, there's a labeling which satisfies every single edge in the graph, and instances in which at most a beta fraction of the edge constraints are satisfied. So what do we know about this problem? So standard NP completeness tells us that gap, we've written it gap 1. So to distinguish between things which are perfectly satisfiable and not perfectly satisfiable is NP complete. This is and in fact, when it's not perfectly complete, there's a small gap. There's sort of like an inverse polynomial gap. And if the number of clauses is n, it's not as if it's 1. It's 1 minus 1 over n. So this is NPHard. This is just restatement of the Cook-Levin theorem. And then what happens, so this I'm just stating regular Cook-Levin theorem. Now let's state the main results of in the world of PCPs in this language, what has happened since then. So I'm going to talk about the PCP timeline. So the celebrated PCP theorem from the early 90s, Aurora Safra and ALMSs, states that this gap that you have between 1 and 1 minus 1 over n can be expanded. Right now, it's just an inverse polynomial gap. You can actually, the PCP theorem states that this can be expanded to gap 1.999 LC is NPHard. This is an alternate formulation of the PCP theorem. It says, distinguishing between label car instances which are perfectly satisfiable and those in which at most 99.99% are satisfiable is NP complete. So it says, so the PCP theorem says, the way the original PCP theorem is, it shows there is a constant close to 1 for which this is true. Well, I'll come to it. That's going to be the main focus of the talk, how small. Make it so, the big thing about the PCP theorem is this was an inverse polynomial gap between these two numbers. It blows it up to a constant gap. Small, but constant gap here. So n will be the size of the instance. So if for over here, so when I mean NP-hard, what do we typically mean? We just, at the heart of it, it just says there's a reduction from 3 sat. So it's an instance size of 3 sat. So so n will always refer to the instance size given there. So each of these is this is just stating there's a reduction from 3 sat to label cover. And another way of stating this is just stating there's a reduction from 3 sat to label car instances, in which if the 3 sat instance was satisfiable, the corresponding label car instance is satisfiable. If the 3 sat instance was not satisfiable, note that if it's not satisfiable, all you know is every assignment violates at least one clause. However, the corresponding label cover, every assignment will at least violate a 0.001 fraction of the edge constraints. So this was the PCP theorem. Already this blow up of this gap was useful to prove a large number of, show inapproximability of various combinatorial optimization problems. Now, just as Sagnik asked, you can ask how large can this gap be made? And in fact, subsequent work, due to work in the repetition theorem of Fege-Killian, 94, and Raz finally in 95, showed that this gap can be made as large as possible. That is, right now it's just a small constant gap. You can make it as close to 1 as possible. In other words, for all delta, gap 1 delta label cover is NP-hard. NP-hard. And in fact, and the reduction, so the NP-hard means there's a reduction running there, and the reduction runs in time n to the order log 1 over delta. So repetition theorem basically gave us this one, that is, you could blow up this gap. It was a small constant gap. The PCP theorem said there's a small constant gap, said you can make the gap as large as you possible, basically all the way up to 1. For every constant delta, you can make this gap. And notice you can only make this for constant delta because the reduction runs in time n to the order log 1 over delta. You can't make delta to be super constant if you want polynomial time reductions. Yeah. It's not NP-hard, it's NP-hard under reductions. Yeah. What I would, am I making, that's fine. So we were actually interested is, next big thing, so when I'm talking about PCP timeline, I'm talking about, so this is a starting point for various hardness of approximation problems. I'm not going to be talking about the consequences of these. These have, for various problems, max cut, vertex cover, you have consequences of this. I'm going to be talking about what's the improvement in the hardness of this problem that has happened over several years. And how has that happened? So this is, first it was a PCP theorem which showed this gap. It was not, PCP theorem was not originally stated in this language. But if you want to state in language cover, this label cover language, this is how you will state it. Similarly, repetition theorem says that that gap can be blown up. What we would like to ask further is, can this gap be made even larger? Right now, it's any possible constant less than 1. Can I make delta even sub-constant? And that took nearly a little more than a decade. So sub-constant error. PCPs, it said that Let me actually. For all delta greater than 1 over poly log n, gap 1 delta label car is NPHard. In fact, and the reduction runs, is this too? If can everybody read this? Runs in time n times poly 1 over delta. Poly 1 is x plus 1 over delta. So this is a result due to, this is a theorem due to Moshkowitz and Raz from 2008. So you could make this gap even larger. You could make it as small as 1 over poly log n. And this improves our state of understanding of, you can prove even better in approximability results using this one. Notice that this is better than this because not just the fact that the gap is now even larger, but that the running time of this reduction, as the delta used to go smaller and smaller, this reduction, the running time, the polynomial used to go larger and larger. Here, the effect of delta is not in the exponent, it's only over here. So it's actually, if delta were a small subconstant, this is a nearly linear time reduction. So this is reduction, this reduction is becoming larger and larger polynomial. For small enough delta, this is actually nearly linear time reduction. So you get nearly linear time reduction. So this reduction result of Moshkowitz-Raz is better than the one you get from repetition theorem in two ways. Firstly, you can achieve much smaller delta, and secondly, the reduction is much more compact. It's the new label cover is just linearly large than the old 3-sat instance. It's not such a huge, its size is not so large compared to the original 3-sat instance. And this is the current state. This is the best thing which we know today. It's conjectured that you can improve this even further. You can actually get to up to inverse polynomial error. This is what's called the sliding scale conjecture, and there's been work in this direction. The most recent work which I was mentioning is towards that direction. We don't yet have the conjecture, but we know how to, there seems to be some progress of trying to get A delta to be even smaller. So let me just write that. So possibly future is the sliding scale conjecture. Delta to be 1 over, say, so poly n. It's unclear if this is doable or not. There's been work towards that direction. And so what we'll see is how does one go about proving these results. So these are typically stated. So label car is a language in which you state this in order to prove a hardness of approximation results. But to actually prove these, usually all these are stated in the language of probabilistically checkable proofs. So for the next 5-10 minutes, we'll sort of move to this one and see how these PCPs imply these sort of label cover results. Any questions so far on the statement?
So if you take the last result where delta is 1 over polylog, if you apply the same proof technique to prove delta over 1 over poly n, will I get a big hit on the reduction time?
It will hit there's both a hit on the, this reduction time firstly becomes large. More than the reduction time, there's another factor I'm hiding here. You'll have to talk about the size of the alphabet, which I have not been mentioning at all in any of these results. So the size of the alphabet for these results to be useful for hardness of approximation, the size of the alphabet should be polynomially sized. If the alphabet size is super polynomial, you won't be able to use this. And the reason this stops at polylog n is that's when the alphabet size is. Once I go more than polylog n, the Moshkowitz-Raz reduction forces the alphabet to be super polynomial and renders it useless for hardness results. I'm not mentioning that explicitly, but
Is
Is there any simple algorithmic consequence, like if the sliding scale conjecture is true, you can see some clear improvement in a simple example? Or
I don't have a simple, but there are problems. For example, there is still recently set cover required sliding scales to prove optimal hardness of set cover. The ln n hardness of set cover, we needed this, but now since last year, due to alternate work of Dinur and Steurer, now we know a different way of trying to prove hardness of set cover. But multi-way cut to show the optimal hardness one needs, that's actually equivalent to the sliding scale conjecture. But it's not an obvious action. So far I've stated everything in the language of label card. Let's go to what are PCPs. So PCP is a characterization of NP, and it states the following. It says, in the classical NP proof, you're going to check that some formula is satisfiable, and the way you do it is there's a deterministic verifier which reads a classical proof, an NP proof, or an assignment. It reads every bit of the proof to check if it is actually a valid proof for the formula or the theorem that you're trying to prove. PCP says that any such proof can be rewritten in a possibly slightly longer format, such that now, instead of a deterministic verifier, we have a probabilistic verifier which probes this proof at not in its entire location, but at a very few locations. So it's a very local verifier. So I marked it as a contiguous, but this need not be a contiguous location. It could be just a few locations over here, and then makes a local test on this view of the proof and accepts whether the proof, whether the local view of the proof passes the local predicate and accepts it, not. And basically, this is the sort of completeness and soundness you have of this proof system. If the original theorem was in fact true, if the formula was satisfiable, there is one such proof such that all the local views are accepting. And if the formula is not satisfiable, then no matter which proof you give me, which purported proof is given over here, most local views are in fact rejecting. So let me actually write this a little more formally. So PCP, so completeness states that if phi is in SAT, there exists a proof such that for over all randomness, the local view of the proof, this is what I'll call the local view of the proof. You're looking at a local view of the proof, passes the local predicate with probability 1. And soundness says that if phi is not in SAT, then for all proofs pi, the probability that the local view, by pi QR I mean just this part of the proof, this part of the proof satisfies the local predicate is at most some constant delta. Huh?
The randomness is over which places I put.
The verifier is going to toss some coins. That's over the random coins of the verifier. And the PCP theorem just states that every such proof can be rewritten in such a way such that the verifier tosses at most logarithmically many random coins and makes at most, in fact, the window is extremely local. It just queries a constant number of bits of the proof and is able to do this, has that completeness and soundness property. Fine so far. So this is stating the PCP theorem now in the language of proofs. Here I have stated PCP theorem in the language of label cover. So in this language, PCP just states this proof is sort of a locally checkable encoding of the NP proof. That's a mouthful. If you don't follow it for now, we will come back to this fact later. So far I talked about the PCP theorem in two languages. One I said it's hardness of this problem. Another I said that it's stating that every proof can be rewritten this way. And I want to say these are exactly the same notion. There's in fact no difference between the two. So let's first see that. So we talked about PCP theorem one in the language of, first in the language of label cover, second in the language of PCPs. In fact, I'll show that this is not just one implies the other, they are actually syntactically exactly the same notion, what I'm talking in both these things. So let's see, let's suppose somebody gives me that gap label cover is NPHard. Let's first show that there exists a rewriting of every classical NP proof in this format. So suppose you're given an instance of label cover, and we know that it is NP-hard to distinguish between things which are perfectly satisfiable and 0.99 satisfiable. So there's a reduction from SAT to such label cover instances. From that, how do I compute a PCP for SAT? And I think the process is just that. There's nothing more going to happen for there. So because what I'm going to view is this. So recall in the label cover definition, there were two sides to it. One was the large side, and on the small side, there was projection constraints going from large vertices to small vertices. When you come back to the proof, and I'm going to view this as a proof, the proof is just going to be the small side. It's going to be the proof will just be the assignment to the small side. And what will be the verifier? So I'm given a SAT formula. I want to come up with a proof for it. So the first thing the proof will do is it will just do the reduction to label cover, and then expect as proof not the assignment to the SAT formula, but the assignment to the left-hand side of the label cover instance. And how will the verifier check that this proof is a valid proof for the SAT formula? It will just pick a random big vertex, that is a random left vertex, query the entire neighborhood of that left vertex, and accept if there is a value for an assignment for this guy that satisfies all the labels to this vertex. So these are, is there a label to this such that all the projections are satisfied? If that is satisfied, then it will accept this local view. So this is very much, notice it's a very local view. If the degree of that label cover had been a constant, this PCP is reading only a constant number of locations in the proof, and have that it has the properties. If in fact the SAT formula was satisfiable, then you know that there is one labeling that satisfies all the vertices. Therefore, in the S instances, all the views are happy. So in particular, it will satisfy all the local view. Every local view will satisfy every local predicate. What happens in the no instance? No instance, we know that the number of edges that are satisfied is at most delta. That's what the label cover instance gives us. So in fact, the average view is very unhappy. So if you look at it, that is a view from a random window is at most delta close to a satisfying view. That is, if you look at most edges, there is no, give me any proof here, no matter what you do here, you will only satisfy delta fraction or 0.99 fraction of the edges. That's what the hardness of label cover says. And in fact, this is stronger than what we want. We want the fact that just the local view satisfies the local predicate with probability at most delta. This, in fact, gives you the stronger statement. It says that in the S case, there is one labeling such that every local view satisfies. In the no case, even the average satisfaction is very small. So stronger than what we want. So in fact, let me just straight the stronger. This one, this is usual soundness. The robust soundness is what we actually get. What I'm going to say is for all proofs pi, the expected agreement between the local view and the satisfying assignments of the local predicate is very small. This delta is 0.99 if one. So this is what you get. So if I have that statement, then I have a PCP which has this stronger soundness property, and this soundness property actually is a much stronger soundness property than this property that I want. This states that the number of views which are completely satisfiable is at most delta. This says not just completely satisfiable, the fact that a view has even some agreement with the satisfying view is at most delta. Is this clear or is huh? That depends on what the degree of this label cover is. So the label cover produced in this the PCP, this part is actually constant degree label cover. Constant degree label cover. I should have specified that, and hence this will be a order, queries will be order 1. And notice the randomness will also be logarithmic because this instance size is polynomial. Therefore, amount of randomness to pick a vertex will be just logarithmic in it. So what I've shown is if you have PCP theorem of this form, it implies the PCP theorem of the other form. In fact, it implies with a stronger soundness. So I'm actually now going to cheat. I'm going to say we are going to actually, even the other PCP theorem, I'll say we'll assume the stronger soundness. And notice that this is then it's actually an equivalence. If I had a PCP with this completeness property and this soundness property, I could the next slide I want. So suppose, so this is what most, I'm going to skip this slide. So this says that if I have this label cover and I have a PCP of this form with the stronger soundness property, if I have a PCP with a stronger soundness property, it's just easy to check that this process is actually invertible. You have a stronger property, you create a label car instance in which each vertex here is corresponding to the random coins, and then you put edges only if those random coins probe those locations and have exactly this process. This is actually an invertible process between PCPs and this one. You can do this check. It's a syntactically, these two things are exactly the same. So this PCP theorem and this version of the PCP theorem and the PCP theorem with this completeness and this robust soundness are actually exactly syntactically the same object. There's no loss of parameters in moving from one version to the other. Why am I doing all this? Because I don't want to be talking in language of label car. I want to talk in terms of PCPs for the rest of the talk. So now I'll forget about this and I will talk about how to build PCPs for the rest of the talk using composition. Huh? How do you label the edges, meaning? So the constraints you mean. So constraints will be this. So what will be the? This one here, the label here will be, I'll give a label to all the randomness, I'll give a label to all the vertices over here such that there exists a single labeling such that all the projections are satisfied. So the label here to this, when I go from the proofs to this one, the label to this vertex will be the label of its entire neighborhood such that, such that they are all consistent. So basically it will be a member of SAT CR will be, I'll tell you, give you a member of SAT CR over there. So it's not fully, so it's what I said, I cheated stating that regular soundness is, so robust soundness is stronger than regular soundness. So you'll have to use, there's a slight weakening of parameters. So what we'll now, but what you can see is all constructions actually yield robust soundness. Therefore, in the previous ways in which this transformation was done, there was a loss of parameters, but if you actually go into the construction and see, you actually get the stronger soundness property, then there's no loss of parameters in going between the two. You had a question? So these two are equivalent statements. That is PCP, there is a PCP for SAT with robust soundness error delta, and there's a reduction from SAT to gap 1 delta label cover. These are exactly syntactically equivalent statements. And what happens here is the alphabet size of the label cover is roughly exponential in the number of queries. This is Rahul's question of the number of queries of the robust PCP. Because it's going to be an element of SAT CR which could be as large as this. Okay. So now, okay, so far fine. So we wanted to construct label cars of this one, which means I want to construct robust PCPs with this stronger robust PCP property. So how does one go about doing it? And one in sort of essential ingredient in almost all in every single PCP construction that we have seen so far in all these constructions is composition. So what I'll do in the next 5-10 minutes is understand what is composition, why is composition required, and try to give an idea of how composition works while trying to construct such PCPs. So let's look at this PCP. So what do we want a PCP? We want to construct a probabilistic verifier that reads very few locations and yet be convinced of the veracity of this proof. And what does it do? So the verifier's actions are basically this. It has its input, the formula, and then it has some local random coins which it's going to toss. Based on this, it's going to compute a local window I and a local predicate F, read the local view, and accept that the local view satisfies the local predicate. So suppose, to begin with, I was not able to get a PCP which gets a very local view. So the original NP theorem says that this verifier, if it reads the entire thing, this is doable. That's a classical NP completeness result. Suppose, to begin with, we were able to reduce that locality from n to square root n. PCP theorem says that you can reduce the locality all the way down to a constant, but suppose you were able to do it to square root n or something of this form, then let's see, can we do better? I want to say this is where composition comes. So already square root n is something non-trivial. I do not know how to do it. Classical NP completeness says you need to read the entire proof. You have to see every single bit to be do. But suppose you could make it something smaller, then what could we do? Then the idea of Aurora and Safra is use this object recursively. So you need to check that this square root n location satisfies some predicate. And the idea is I want to check it using, I don't want to read all of it to check that it satisfies the predicate. A PCP theorem is precisely this. It checks if a theorem is true without reading its entire proof. So conceivably, I could use another PCP to check that this local view satisfies the local predicate without reading all of it. And they said compose. Try to compose it with another PCP verifier. Say to reduce the locality from root n to fourth root of n and keep doing it this way. And this is where composition enters the picture. So they said just compose. If you have some sort of initial PCP which will reduce the locality slightly, you could in principle compose. This is easier said than done. There's a big consistency issue, and we'll come to it exactly. I'll come to this. Compose is an idea. It's a great idea of Aurora Safra. That's the main contribution of Aurora Safra in the paper. We'll see that. We'll see how exactly this can be implemented in the next few slides. Any questions? So, yeah, so I'm going to be borrowing slides. This talk slide is from a mixture of two different talks. So far the proofs have been horizontal. So suddenly, for the next few slides, the proofs are going to go vertical. Apologize for that. And the color choice also, when I put the slides together, it turned out miserable, and I didn't have time to change the colors. So now the proof. This is the proof. So this is the original SAT formula. The verifier wants to check that this SAT formula is correct or is satisfiable or not. So it reads the SAT formula in its entirety, and then it probes this proof at a few locations to check if the proof is correct. This is the usual way. And say we have managed to construct a PCP. So let me. So one of the first. Where should I write? This is the first building block. So this is a Reedmuller code based. PCP. So in fact, I had said that you can reduce locality from n to root n. If you use a Reedmuller code, what you can actually reduce locality, you can make the locality to go as small as polylog n, keeping the proof size, the number of randomness to be order log n. This is the entire work on interactive proofs gave such a thing. So you could, in this one, there were ways in which if you use a Reedmuller code and sort of encode the original assignment using a Reedmuller code, you could get down locality to polylog n. But the PCP theorem says you could push it even further to constant. So how would one do that? So let's see. So let's look at what we need to do actually. So this is a small local view, say polylog n view or a square root n view. I want to do it even smaller. So what do we need to actually check? I need to check that these local bits satisfy some local consistency test without reading all the bits completely. And as I mentioned, the idea is to use a PCP verifier to do this, another PCP verifier to do this process. What does that mean? So that means this following. So you have this. I wanted to check that this local view satisfies some predicate, local predicate. So you have another. So you now construct a language whose accepting instances are exactly the accepting instances of that local predicate, and construct a PCP verifier for that one. So it's going to check if this is a satisfying instance of that instance by reading its own proof. So this is going to be the combined proof. Let's see if this works actually. So there's this first, the outer PCP verifier, which wants to check that this SAT formula is true or false. And the way it does it, it's going to, in principle, it's going to read this proof, look at a few locations of it, and it's going to check if that few locations satisfy the predicate. But it cannot afford to read these locations because these are too many in number. So it decides to hand over control to another proof, another verifier which is going to read these locations and with the help of an additional proof. But notice that actually the locality has not increased because the other proof, the way I have defined PCPs, this object needs to read its input in its entirety. So this object here, the verifier, though it readed the proof very locally, the input it had to read it in its entirety. The SAT formula it had to read completely. So the input for this guy over here is this local view. So it's actually not what I want to do, I want to read even less than this, but the way I have written it right now, it needs to read the entirety of this. So it doesn't really achieve what we wanted to do. I wanted to check this process. So suppose we could strengthen what a PCP means. So PCP states that you can check a proof by reading only very little of the proof. Suppose we could strengthen this further. I could check the veracity of a theorem without even reading the entire theorem. Suppose you could do this. Seems far-fetched. Then possibly you could then this process will work. So we'll actually go ahead and define this new notion. So you want to check that a particular SAT formula is true. It's encoded in some format. Earlierly the verifier was reading the SAT formula in its entirety, but now it's going to probe even the input at a few locations and then going to do this combined process. But it seems quite bizarre to expect such a thing to be able to distinguish things which are in the language from outside the language, because things which are in the language and outside the language can disagree in just one location. And there's no way I can distinguish them by just probing this one. So we will change our completeness and soundness requirement the following way. So I'm going to define something called PCP of, it doesn't check if something is a proof, it checks if something is proximal. It doesn't check if the theorem is true or not, it checks if the theorem is close to being a true theorem or not. So this is what I call PCP of proximity. So it will say if phi is in SAT, you will have the same thing. Now you are not only going to take a local view of the pi and this one, you are also going to take the local view of both the input and the proof. And soundness, what we will strengthen it is in the following sense. This is phi. We won't be able to say if phi is, so earlier soundness of phi was not in SAT. Now I'm going to replace it and say if phi is far from SAT, in other words, that is the distance of phi from SAT is large, then for all proofs pi, yeah, so now, the previous robust soundness comes in. So what the previous robust soundness says? It says the local view either is satisfying or far, or an expectation is far from. It's not saying it is true or this one. It is actually either satisfying or far from satisfying. So once you have the stronger this one, these two objects now very nicely just compose with each other. They just syntactically fit in with each other. So we'll have this other object which I'm going to call PCP of proximity. And the only thing that's happened in this one is I changed the definition of PCP twice along the course. First I changed soundness from regular soundness to robust soundness. That's in how the output behavior was behaved. I changed the input behavior from checking if a theorem is true or not to checking if a theorem is true or from close to being true. So this is PCP of proximity. And the only thing to notice is all existing constructions have both these features. They can easily be altered to have both these features. Once you do this, it's easy to check that composition now just syntactically just goes through. So you want to check that this theorem is close to being true. So you have an outer verifier which probes a very few locations. So instead of it reading all the locations, it transfers control to an inner verifier. The inner verifier is this theorem is actually these locations put over there. So it just makes a few probes into its locations and then checks if the whole thing is true or not.
Delta over there is just what? It's the number of bits or something?
No, so there's some notion of distance. So you're going to guarantee if things are far in a particular language, then it's a proximity parameter. So you say that If in the language you satisfy it, if things are at least 1/3 far away, then the proof will always catch local ones. It's closer than, so delta is some fixed proximity parameter. Think of delta, say something like 1/10 or something.
In what measure?
So right now, the way it's done is there's some encoding of the SAT formula and it's Hamming distance.
So how is robust soundness helping us?
How is robust soundness helping us? So recall, what does robust soundness tell you? So usual soundness tells you that the local view is either satisfying or not satisfying. Robust soundness tells you either the local view is satisfying or itself far from satisfying, which is exactly the input to the next guy. The next guy is saying either robust soundness guarantees that the local view is satisfying or in fact it's far from satisfying. PCP of proximity in principle just distinguishes between these two objects. It distinguishes an object which is satisfying and things which are far from satisfying. So the input-output behavior of these two objects exactly match. And hence, if you have a robust PCP of proximity, you can just compose it with itself.
So what is the consistency issue you mentioned before?
No, so consistency issue what I mentioned before is, so what was the consistency issue? So notice that this is for a particular choice of coins, random coins of the outer verifier. Now if it makes another different coins of random coins of outer verifier, it's going to do, so the way I have defined it now, consistency is completely taken care of. Where composition was done in the past, prior to this work, what I'm saying now is work that happened in 2004 due to joint work with Bensasan, Goldreich, Sudan and Vadan, and independently by Dinur and Reingold. Prior to that, the way composition happened, the original proof theorem, you had to check there was a consistency issue that, because they didn't have robust PCPs and PCPs of proximity then, they had to do a finer way of saying that this inner verifier is talking about some local bits here. This inner verifier is going to talk about some other local bits here, and local view here. These two local views could be agreeing at the same location, but they should be agreeing. You need to check that these two are consistent in the old way. The way I had defined it right now, there is consistency just is taken care of automatically by the way. Once you define robust PCPs of proximity, consistency is guaranteed by the definition.
No, I guess what's a little bit confusing to separate these notions is that PCP proximity is weaker than PCP, while robustness is a stronger condition. It's not really good.
Why is PCP of proximity weaker?
It's insisting that the proofs are relative in their power, and soundness condition is not.
Yeah, so but this is true for every NP complete language. So I can always assume that I take the input SAT formula, I encode it, and then give it as.
Yeah, so we're using within.
No, at the very first. So I agree. It's a weak. So this seems as a weaker this one, but you can always show that if I have a PCP of proximity, there will be. If I have a PCP of proximity for SAT, I can get a PCP, regular PCP for.
No, but I thought that what you were interested in was the query input, and that's why you define it.
Very complex.
Like how much of the theorem you're reading. I mean, I thought that's reading theorem.
Yeah, because I want. That's one way of looking at. Yeah. No, but
that's kind of. I mean, like when you compose it, right? The proof becomes the input.
The proof becomes the input, and you want to recheck that the input is. You don't read all of the input. Therefore, I define a PCP of proximity.
Yeah, but it's not being. It's kind of implicit. The query complexity of the input. So the query complexity of the PCP becomes the input. The definition of PCP of proximity somehow captures that.
Yeah, it gets hidden into the.
There's one comment.
No, it's just so this definition of robust PCP and PCP of proximity is just to make things nicely syntactically fit in. So it really didn't matter how I built the outer object, how I built the inner object, as long as I guarantee that the completeness and soundness satisfy this property and it had robust soundness, they just syntactically just fit in with each other. And that's how composition works. So in principle, you could take this Reedmuller based PCP and just keep on composing it with itself. Each time you would. So if each time you compose it with itself, you'll move from polylog n. The first time you compose it will become polylog log n. The input size is now gone from n to polylog n. So next time the theorem size drops to polylog log n, and if you do it k times, it goes polylog log 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 k times. You can reduce it. Notice that it still doesn't get you the final PCP theorem because you do it a constant number of times. It becomes smaller and smaller, but not yet a constant. And for that, you need the Hadamard based PCP, which Notice I can't do this a super constant number of times because then the randomness blows up too many times. I can only do this a constant number of each time. I will add an extra order log n randomness, and I can't do it super. If I do it log star n times, certainly it does go down to constant, but I can't afford to do it super constant number because each time the randomness will be log n. To it, Hadamard-based PCP is a PCP in which the query complexity is order 1, but the randomness is huge. It's order n square. It's unlike this. But the point is, once you're deep into the recursion, the input size is so small you can afford to kick this in. And in fact, this was how the original PCP. So Arora and Safra had constructed a Reedmuller code-based PCP and done composition twice, stopped it with that. The main contribution of ALMSs was a Hadamard-based PCP. They said, do this twice, compose it with a Hadamard-based PCP code, and you'll get the final PCP theorem.
So by composition, how the error will go?
So if you actually check out the parameters, the error will just be additive. So if this was one, so if this was one, let's write it as 1 comma 1 minus delta. Rather this, if I write this error as, instead of delta, if I write it as 1 minus epsilon, if the outer had error 1 minus epsilon and the inner had error 1 minus epsilon prime, the composed will have error 1 minus epsilon plus epsilon prime. The deviation from 1 will grow additively. And that's just union bound.
So the proofs for all the levels in the recursion will be given by the prover, right? So the prover will have a new proof.
So the proof is basically going to be, what is the proof? Notice that the proof.
You will have a.
So the proof is basically now it's just the inner verifier. Notice the outer verifier is not reading anything. The outer verifier is completely handing over control to the inner verifier. The inner verifier needs to read its proof and these locations, but these locations are actually locations over here. So the composed verifier's proof is the outer proof and all the inner proofs. So that is the proof for the composed verifier. And this is what we call composition. So it's a composed verifier which simulates the outer verifier to find out which queries it's going to read and then just hands over control to the inner verifier, which is going to probe locations from the outer verifier, but it's going to check that those locations satisfy the outer predicate by probing some more locations from its corresponding proof. And there will be a different inner verifier for every outer predicate. So there will be a sequence of inner proofs, and this will be, the whole thing together will be the proof for the combined verifier.
So you have an inner proof for every choice of a local.
For every choice of, yeah.
So aren't there too many local choices of local?
There are only logarithmically many random coins. Therefore, the number of things, this will only be polynomially large, and hence this proof will be only polynomially large. It's polynomial in the old proof. So one way you can keep counting proof length, but the easiest thing is just count the randomness. Randomness is randomness of this guy plus the randomness of this, so it's just sum of randomness.
But it will not give a linear length.
No, it could give you a linear length proof. If it won't give you linear, it will give you, you could get nearly linear. So in fact, so this composition, so when we found it, it was previously composition, there were other processes. We actually did it to eliminate the other, there were other processes that were happening in between to do this consistency between outer and inner. And in fact, you do get nearly linear proof length. You won't get linear, but you will get nearly linear in this process. I'll take this off. Questions? So this gives us this proof. And of course, to go from here, you could apply, to get, this will give you 1 to 0.99. And you could get, repetition theorem will tell you how to get it to 1 to delta. But what I would like to do is, in this strategy, can I get even better? And I go all the way here. And if you actually look very closely at this proof, you can never get something delta less than half if you do such a composition along the way. And why is that? So notice that this delta, the soundness error which we got, was exactly this delta which we had here. This, I actually changed this expected soundness. For all proofs, this is what we had. I should have written this, not the other one. The agreement of x pi that delta over there was exactly this delta, robust soundness. I want to claim that you can never get robust soundness less than half if you do such a composition procedure. And basically what is that? That is the agreement of the local view, which now comprises of two parts. There's a local view there's a part in the inner proof, and there's a part in the outer proof. And you want to say the expected agreement of this local view with a satisfying predicate. Each of them can individually be always completed to a fully satisfying local view. Therefore, the expected agreement will always be at least a half. It can never be less than a half. So this sort of, if the proof is logically split into two parts, an inner and an outer proof, you'll always be hit with this problem that the delta will always be greater than half. You will never get a delta which is less than half. And so such a theorem is not achievable by, even if you had building blocks which were much better off, such a theorem you can never achieve it if you're going to use such a composition step along the way. Another 7 minutes more, so let's see how we can do the composition in the. So what we'll notice is this finite theorem is also got, in fact, by a composition theorem. It's a different composition theorem which happened. In fact, it's the same building blocks that were used, and it's just the composition. The only new feature of this proof is a composition theorem, a different composition that goes into proving this. And how does that happen? So for that, we'll have to change our object a little more. What I will now define is not just a PCP of proximity, define what is called a decodable PCP. And a decodable PCP is very similar to a PCP of proximity. So what was a usual PCP? A usual PCP was just an encoding of the NP proof. It was a locally checkable encoding of the NP proof. A decodable PCP is going to be one extra feature. It's not going to be just a locally checkable. It's going to say that this proof contains in its belly the original NP proof. So in particular, if I want a particular symbol of the NP proof, I would give it as an input a J and say, tell me that symbol. It is an encoding, so in principle it does contain this proof is sitting somewhere over here. I'm going to make it more explicit. A decodable PCP is exactly this object. It's an object in which, in addition to its original input, the verifier not just gets the formula and its randomness, it also gets an index into the NP proof. And then it's asked to either reject if the local view is rejecting, or to return what would have been at that location in the NP proof. And let's not define completeness soundness. It's what will be obviously the obvious definitions. For want of time, you can define it suitably here. So given such an object, how do you compose such a one? By the way, the proofs have once again become horizontal. It's back to different slides. So there's an outer verifier which is going to look at this location of the proof, and it's going to check if it satisfies a particular local view. So instead of checking that this local view is this one, it's going to hand over control to an inner verifier, which is going to check it. But instead of just handing over control, it says, return to me a location in the outer proof. Decode to me the value of this outer proof. So decodable PCP is, let me just go over. So again, it says, it's similar to a PCP, except now it will return a value in the original NP proof. It's similar to a PCP, it's going to also return a value in the original NP proof. This is a slight definition. I'm going to make a change in the definition of PCP proximity. Say it's going to do this extra process for me. Because I realized the composition with PCP of proximity will not fetch me this object. Now, how can I do composition with such a object? So you will take an outer proof, and I want to check that this local view satisfies a particular predicate. So instead of it, I'm going to use an inner proof and read a very small local view in the inner proof, and expect it to decode a symbol of the outer proof, and then check that symbol is in fact, read that symbol in the outer proof, just that symbol. Instead of reading the outer proof in its entirety, read just that symbol and check that the consistency is passed. And that's the entire composed verifier. The composed verifier decides which local view of the outer proof to read, doesn't read it in its entirety, just picks a random symbol in it, goes to the inner verifier, asks it to check it, and then decode to read the outer one, because this is the input to the outer one, and then it just reads that one symbol and checks if that is the decoded value from the inner guy. The question is, This certainly is, the query size is considerably increased. It's just this inner query plus this one outer query. It's not the huge outer query. But the question is it robust? Does it have robust soundness? And we needed robust soundness, not regular soundness. And once again, the reason it will not have robust soundness, the proof composes of two parts. It has, for exactly the same reason, the proof composes an outer proof and an inner proof, and it can never have soundness better than half, because each of the proofs individually can be extended in my view. So what will we do over here? I'm sorry if I'm going a bit fast. So what we'll do over here is that we'll define a new composition theorem. So what's the moral of all these problems is, as long as there are two proofs, an outer proof and an inner proof, you're going to run into problems. You will never get delta less than half, because each of them can be individually extended to complete the proof, and robust soundness can never become better than half. So you'll never forget about this theorem. You can't even achieve this theorem using a composition technique. So if you have this logical split of a proof into two parts, you can't do it. So we'll do a new composition theorem in which there's no logical split of an outer and an inner, but yet it will be a composition of an outer proof and an inner proof. So how does this work? So this is the outer proof. So just let's pick a random location in the outer proof and look at several outer windows that contain this location. So these are all various outer windows that contain this location. There are several, this location participates in several outer windows. Let's look at all these outer windows and look at all the corresponding inner proofs in which, so for each of these outer windows, there was a corresponding inner proof. Let's look at all of the inner proofs and expect them to decode this outer symbol, because they are corresponding to the windows which contain it. They will all, in principle, decode this. Expect them to decode. And then, instead of checking them against this one outer proof location, check them against just each other. So there is no outer proof in the new composed proof. It's just it's in the eyes of the verifier. The outer proof, there are only inner proofs. Each of them is going to check just local views of the inner proof. Each of them is going to, in principle, decode this, but it's never going to read this. It's just going to check these guys against themselves. So there's only one inner proof. It's just the concatenation of the inner proofs, which is the proof of the composed guy. So you get rid of this problem of this proof being split into two parts. And that's the composition theorem that happens here. You just accept if all the inner viewers accept, and all their answers actually decode to the same value. And this happens to give you composition. And in fact, if you do composition this way and the same building blocks, you get the subconstant error. You can completely avoid the use of parallel repetition theorem, and you get the stronger statement. Apologize if I've been too fast. But here it's just a different way of doing composition. It's the old way of doing composition. There's been a different way of composition. So it's strange that this theorem has actually there is actually no new building block element in this proof of this. It's just a different composition technique which gave us this fact. The building blocks were exactly the building blocks which occurred in the late 90s, which were used to construct this theorem. It's just a different way of doing composition that fetched this theorem. So it's conceivable that a still better way of composition can actually give us the sliding scale conjecture which did. And in fact, the most recent theorem which we have is we have a different composition, and we use the same building blocks, which gives us a step towards the sliding scale conjecture.
This new way of composition gives you the same as MR08.
So this composition, MR08, don't write it this way. This composition is due to work by myself and Irit. And what we show is, if you had, they also do a composition theorem and build different building blocks to do it. What we show that if you use this composition and existing building blocks, you'll just recover their result. So it's not just the heart of the result. Their result is just a composition theorem. You don't need any new other technical building blocks. It's just once you have a composition theorem that directly implies this one. Let me stop with this.